Welcome back to The Explainer. I am so pumped to get into today's topic because we are about to completely reframe how you think about agriculture. We aren't just talking about traditional farming today, we are diving into the highly precise engineering discipline of architecting biological systems. If you've ever wanted to understand how life can be designed, managed, and scaled with blueprint-level precision, you are in exactly the right place.
It's a breathtaking macro view of a fully integrated biological architecture, literally a perfect visual representation of how we can predictably harness nature. By utilizing highly controlled environments and strict standard operating procedures, we aren't leaving success up to chance or the weather. We're engineering ecosystems from the ground up, turning biological variables into highly reliable, productive engines.
So here's our roadmap for The Explainer today. We're going to establish the universal framework for architecting life, and then tour 5 distinct biological engines: cultivating fungi microclimates, engineering aquatic systems, exploring poultry architecture, extracting wild harvests through sustainable forestry, and finally, evaluating which engine actually fits your needs.
Okay, Section 1, Architecting Life's Blueprint, the 4-step framework.
No matter what species we're working with, system design relies on this predictable rhythm of intervention. It's a 4-step rhythm. Step 1 is design, configuring the physical environment and those absolutely crucial safety parameters. Step 2, we initiate. That means introducing the foundational biological agent, a seed, a spore, or bacteria. Step 3 is manage, the daily balancing act of the ecosystem, tweaking things like temperature or aeration. And finally, Step 4 is harvest, extracting the yield while keeping the system's integrity intact. Honestly, this is our master blueprint.
Moving right along to Section 2, Cultivating Microclimates for Fungi, the Dark Climate.
So our first engine brings us into the real world with mushroom cultivation. Now, the main engineering challenge here actually isn't sunlight. It's maintaining a totally sterile, dark microclimate. Beneath the surface, this engine is driven by spores, not seeds. This root-like mycelial network expanding through the substrate is basically nature's biological internet. It absorbs nutrients with incredible efficiency, hitting a massive 85% utilization rate. It's a highly controlled, dark climate engine running at absolute peak performance. When we walk through the operational blueprint for fungi, precision is literally everything. Step 1 requires strict sterilization of the medium, just wiping out any competing organisms. Then comes the critical inoculation phase. But check out Step 3, managing moisture. To figure out irrigation needs, cultivators contrast that highly sterile prep with a super manual, tactile method called the squeeze test right before misting. It's this perfect blend of rigid scientific protocol and hands-on environmental management.
Crucially, we've got to balance strict quality parameters against safety guardrails to monitor this whole system. For quality, the thresholds are rigid, locking ambient temperature exactly between 25 and 30 degrees Celsius and keeping humidity pinned at 80 to 90%. But on the safety side, those are completely non-negotiable. Fungal environments demand a pristine hygiene protocol. We're talking zero stagnant water and mandatory personal protective equipment, masks, gloves, the whole shebang during inoculation just to prevent contamination.
Let's dive into Section 3, Engineered Water, Aquaponics, and Pisciculture, Managing Aquatic Biomass. Transitioning from the dark and sterile to the dynamic and fluid, there's a really stark contrast between two aquatic philosophies here. The core mission is turning biological waste into plant fuel and managing living aquatic biomass. In a closed-loop engineered aquaponics system, it relies entirely on a controlled bacterial nitrogen cycle to transform toxic fish ammonia into usable plant nitrates indoors. But then you have open water commercial pisciculture. That relies on optimizing vast, plankton-driven natural food webs right out in open ponds. Same foundational element, water, but two wildly different biological architectures. In the closed-loop blueprint, sequence is literally life or death. System fabrication and water prep obviously come first, but pay close attention to Step 3, initiating the cycle. You absolutely must establish the biofilter bacteria first by introducing a tiny fish load or an ammonia additive. If you just dump a full harvest of fish into the tank before that bacteria is ready, the whole system collapses. You've got to architect the invisible before managing the visible. Shifting over to the open water blueprint, the strategy completely flips. Instead of a biofilter, Step 3 involves actively forcing a natural plankton bloom. We do this by applying very calculated doses of organic manure and cow dung slurry to stimulate the ecosystem before ever adding fish spawn. It's definitely a wilder, but still meticulously calculated approach to prepping the environment. When we compare the operational dashboards for these water systems, a fascinating divergence pops up.
Water chemistry is a shared quality parameter for sure, but the safety risks? Totally different. Indoor aquaponics systems face massive electrical proximity risks. You have to keep water completely isolated from pumps and timers. Open systems, on the other hand, rely heavily on strict adherence to calculated chemical dosing for lime and manure to keep the pond's profile in check. Different scales mean entirely different safety architectures.
All right, Section 4, Spatial Design, Poultry Architecture, the Microhabitat.
Bringing things onto dry land, let's look at poultry. Here, spatial design itself acts as the primary defense mechanism. Every structural element you're seeing has a strict engineering purpose. The elevated flooring and layered rice husk bedding, those are specifically designed to prevent waterlogging. Damp floor litter, or what's known as wet bedding, is a massive vector for E. coli. By architecting the space with suspended feeders and predator-proof window mesh, we're literally building a fortress against disease and predators. Now, looking at the operational blueprint, Step 2 is the absolute critical point: brooder calibration. Young chicks require a highly controlled, draft-free, heated microenvironment for early-stage worth. If this calibration is off, even slightly, the stakes are dramatic. Flock vitality just plummets. From there, it's all about introducing exclusively clean chicks and shifting into daily management to systematically remove threats like that wet bedding. But output metrics mean nothing without safety constraints. Yes, on the quality side, we want tangible results. Eggs with clean shells, consistent size, strong shape. But to actually get there, you need fortress-like safety parameters. You absolutely need strict biosecurity to severely limit outsider entry and enforce immediate quarantine for any sick birds. The architecture only works if the borders are secure.
Moving out into nature for Section 5, Wild Harvest, Sustainable Forestry, Non-Timber Forest Produce. So next, we step entirely out of the built environment and into the wild. And here, the engineering challenge completely flips. It becomes all about extraction without destruction. We achieve this by leveraging existing natural forest infrastructure to harvest resources. In this case, natural lac resin secreted by insects on host branches. The goal here is a sustainable yield, meaning we utilize harvesting methodologies that leave the host organism and the surrounding ecosystem completely intact.
Our sustainable extraction operational blueprint starts with deep site intelligence. We have to identify unpolluted zones and gather meteorological data just to track the ideal harvest windows. From there, it's about managing the host by clearing waste and applying mulch to strengthen the root systems. Finally, in Step 4, we execute a partial collection using specialized tools like sickles to prevent uprooting the host tree. It's just a perfect example of human tools adapting to nature's blueprint.
The standard operating procedures in the wild highlight some really unique safety parameters that you just don't see indoors. Yes, we obviously want site purity and maturity precision for our harvest, but safety out here is its own beast. Ecological respect demands an absolute prohibition on uprooting. Plus, strict fire mitigation is critical. Processing and drying areas absolutely must be kept strictly isolated from open flames to protect the very forest infrastructure we're relying on. And finally, Section 6, Evaluating your biological engine, the capstone synthesis.
We've covered a lot of ground today, from sterile bags to the open forest. But crucially, we need to synthesize all this operational data. This capstone matrix lets you really visualize your choice of engine based on your available inputs and risk tolerance. Just look at the primary vulnerabilities. You can directly compare the risk of competing molds and fungi against power failures in aquaponics, oxygen depletion in pisciculture, E. coli in poultry, or overharvesting in the wild forest. Every single vocation is an engine, and every engine has its specific operating requirements and weak points.
Which brings us to our final thought. Mastering this living blueprint fundamentally changes how we interact with the natural world. So, my question to you is this. Will you continue to view biological systems simply as resources to exploit? Or, armed with this explainer, will you start seeing them as elegant architectures to design, to manage, and to nurture? Think on that for a bit. Thank you so much for learning with me today, and I'll catch you next time.